Oh. Oh.
All right, seems like it's time for us to get started. This is what we have today, Wednesday, and then next Monday. So we're almost toward at the end, and I think I mentioned a few weeks ago that I have kind of a major family emergency going on. Wednesday, I'm actually going to cancel Wednesday's class. I'll let you know on D2L. Luckily, it shouldn't actually affect anything because I have kind of an extra day built in. So you'll just get a free day Wednesday. But then Monday will be the last class, and I posted on D2L with some information about, right, just to make sure you know the last quizzes and such that'll be available. And I'll remind you about that. And remember, there's an ongoing quiz on D2L on Big Bang. See if there's anything else. Any questions? So what we're going to be talking about today is actually something close to my heart because it's what I specialize in, which is dark matter and dark energy. It's actually what the universe is mostly made out of, as best we can tell. And then there'll be one more lecture a week from today on Monday, then talking about kind of life, talking about extraterrestrial stuff like that. The topic of today's lecture is, what is the universe made of? And the answer is that we really don't know. The vast majority of the universe is something that's invisible. We call it dark matter and dark energy. I want to emphasize that when we say it's dark matter and dark energy, that doesn't mean that it's like a cloud of dark dust that makes it, you look out at the stars and you see something dark looking. No, it's something you don't see at all. It's probably a better word would be invisible. Okay. And, right, so we tend to show this sort of pie chart showing what our current best understanding of what the universe is made of. And as we'll talk about, we don't know exactly what it is. We just know that it's there. 71.4%, the majority of this pie is a type of energy. It's not matter at all, it's just a type of energy that exists in space itself. This is the name, dark energy, for something that's causing the universe to expand. And it's in the fabric of space itself, there's energy. But we don't know what causes that energy. So it's an unknown. The vast majority of the rest is something called dark matter. It's a type of matter, but it's not matter like atoms that we're made out of. It's a type of particle that we haven't yet discovered. We'll talk about today why that's not so weird. I don't want you to think that this is some Band-Aid we've slapped on, because we don't understand it. it's actually just pretty mundane, right? We'll talk about the fact that we've discovered dozens and dozens of particles, and this is just one more that we just haven't yet discovered. But every year we're discovering new stuff, and I'll show you a graph of that. So it's actually very mundane. It's like kind of the most normal thing that it would be. Now, most of the stuff that we know of, stars and stuff in planets, even that is not most of the regular matter. The rest of the regular matter in the universe is just that stuff like carbon and iron and stuff we're made out of is only a tiny fraction, as we've learned, of it's mostly hydrogen. Now, when we talk about the visible matter, that's the stuff, right? That's the stuff that makes up about 4%. That's the stuff in this sort of slice of the pie. The visible matter, that's stuff like stars, gas, dust, and again, there's more mass in the dust and gas than in stars. Okay, but this is what we're talking about. We're talking about visible matter: dust, gas, stars. And on the largest scales, if we look out with our telescopes, we see a map of the sky that looks something like this. Now, in kind of orange here, that's what we see when we look across the sky that we're looking through. That's the Milky Way. That's our own galaxy. But if we look through our own galaxy to what's shown in kind of blue here, we see this kind of spider web looking like little dots across the entire sky, representing all these galaxies that we can see. And we say that it looks mostly isotropic and homogeneous. In other words, it looks the same everywhere. Okay? The universe, anywhere we look, it roughly looks the same. And there are literally billions of galaxies if we look out across all of the sky. Okay, so so all in all, about 95% of the universe is invisible. Again, it's not dark is what we call it, but it's probably not the best word. It's invisible. Dark matter is the invisible mass that mostly surrounds galaxies and clusters of galaxies. And we can infer it and study it really, really well. Talk about lots of evidence today. Even though we don't know what type of particle it is, we can see it through its gravitational effects. Dark matter acts like regular matter in terms of gravity, okay? But it doesn't act like regular matter in the sense that it doesn't emit or absorb light. That's why it's called dark. But it's really just invisible matter. And we'll also talk about, we already know examples of invisible matter. Neutrinos are an example. Okay, dark energy is the energy which is causing the universe to accelerate. And it's we say it's dark energy because we don't know what it is, and that it's probably caused by some other particle that we don't yet know about. It's another name for dark energy is the cosmological constant. It's a term you can add in general relativity that causes the universe not only to expand, but to accelerate. Okay, and it's also another word for what we call vacuum energy, the energy inside the vacuum of space itself. Any questions so far? Yes. So first we're going to talk about dark matter in some detail. And first, I know that some of you want more participation points, so I'm going to give you another freebie. So why do we call dark matter dark? And I'm going to give you the answer here. Right? It's not because it absorbs light. It's not because it's dark in color. It's not because it blocks out the light of stars in a galaxy. It's because it emits little or no radiation of any wavelength. It doesn't emit or absorb light. It's basically invisible. So the answer is C. Looks like most of you, I'll give you 5 more seconds. Okay. Okay, good. So everyone got that right. I'm glad. So we call dark matter dark because it's basically because it's invisible. I'm going to kind of quickly go through like some brief history of dark matter. It's interesting in that, right? Like, at what point did we start to suspect that most of the universe was something we didn't know? Well, in the 1930s, so we're going almost 100 years ago, 1930s, people were looking at the speeds of galaxies themselves in clusters of galaxies, and they were going too fast. Some sort of gravity was holding them together that you couldn't, based on their brightness, couldn't have been due to the visible matter. So what we inferred was that there's maybe 10 times as much matter that we just can't see. And at the time, it was assumed to be normal, dead stars, gas, dust, stuff that was hard to see. That's what people assumed it was, right? That's natural. Okay, and that's what people thought for decades. In the 1950s, I put this here because we did find a type of dark matter. It can't account for all of dark matter, but we actually did discover in the 1950s something exactly like dark matter. It's called the neutrino. We've talked about neutrinos. The sun produces trillions of neutrinos per second, and they are flying through our bodies right now without our noticing. They're pretty much invisible, except if we create a huge detector underground, we can detect a few per minute. So dark matter is nothing strange. We already know it exists. It's an example is neutrinos. And then in the 1970s, people were looking at spiral galaxies through telescopes, and it became increasingly clear if you looked at the speeds of stars in spiral galaxies, they were twirling too quickly. Gravity couldn't hold them together unless there was unseen matter. Okay, and at the same time, telescopes ruled out regular stuff. Telescopes ruled out gas because we can see gas. Telescopes ruled out dust because we can see dust. We could add that, and still wasn't enough. So at this point, people realized in the 1970s that there probably was some new kind of matter that we didn't understand, that didn't emit light, that people named dark matter. In the 1980s, there was more new evidence added called gravitational lensing that we'll talk about. People proposed theories besides particles. People proposed theories of modifying gravity. Like, hey, maybe it's gravity that we don't understand. But those theories didn't quite work. So particles, just some new particle, are the leading explanation. And in the 1980s, people started searching for them. That's the sort of thing I work on. Mm-hmm. In the 1990s, totally new evidence. Stuff we talked about last lecture, the cosmic microwave background, gave a precision number to how much dark matter there was. There's about 5.5 times as much dark matter as visible matter. In other words, 85% of all the matter in the universe is invisible. And today, so where we're at today, we're still doing experiments looking for dark matter. Still no one's found it. That doesn't mean it doesn't exist. We'll talk about that. But it does mean that it's very ghostly of a particle. And so one thing I wanted to emphasize is that dark matter, as currently understood, is just a type of particle. And this isn't strange. This is a timeline showing all the new particles we keep discovering. Okay, starting about 100 years ago, we discovered the photon of light. We discovered the electron in atoms. And we've just kept discovering new particles, decade by decade by decade. We just keep discovering more and more. Most recently, the Higgs boson in 2012. Okay, so my point is it's not strange that there's probably dozens of more particles we haven't discovered yet. We just have to build more and more sensitive detectors, and every few decades we'll discover more. Okay, and we think dark matter is a type of particle just like this. That's just hard to find. We need very, very sensitive detectors. So I'm going to go through a bunch of evidence. We're going to talk about individual galaxies, the fact that they're spinning too quickly. We're going to talk about for spiral galaxies, that's very straightforward. For elliptical galaxies, we'll talk about a similar method for it's not that they're spinning so fast, it's that on average the stars are moving too quickly in elliptical galaxies. We'll talk about whole clusters of galaxies. Galaxies themselves orbit each other in big clusters, remember? And if you look at the velocity of those galaxies, they're moving too quickly. They have to be held together by some unseen, some matter producing unseen gravity, or unseen matter producing extra gravity. You can look at the gas in those clusters. The gas in the cluster, again, is too hot. It should be spreading out, but there's some unseen matter with extra gravity holding it in. We'll talk about gravitational lensing. It's a whole other method of determining the mass inside a galaxy. Last time we talked about primordial nucleosynthesis. We talked about the formation of helium and hydrogen in the early universe. That predicts dark matter. Last time we talked about the cosmic microwave background. Now, if you look across the sky, we're still seeing light in any direction we look from the Big Bang. And little temperature fluctuations tell us how much, where the dark matter was early in the universe. And finally, that tells us about the structures in the universe on the largest scales that we see today, like where the galaxy clusters are, that's where the dark matter was early in the universe. It's what pulled things in with its gravity to form galaxies. Okay, so these are the sort of things we'll talk about when we go through the evidence for dark matter. Here's a spiral galaxy. It's the closest major one to us, called the Andromeda Galaxy. And it's a spiral galaxy. All the stars are orbiting around the center, kind of in a plane, right? So they're all orbiting around like this, and we can measure their velocity. And we can use Newton's law of gravitation to figure out, hey, how much mass is in there? How strong is gravity? How fast should their orbit be? And what astronomers use to study this is called the rotation curve. You look at the velocity of stars as you go out from the center towards the edges, and you plot their velocity. And let's give a couple examples of different possible rotation curves. One would be is if you look at a merry-go-round. Now, a merry-go-round, it is just a big disc of steel, right? It's all moving around. You look at like the horses on the merry-go-round. What are their velocities as you move out from the center? Well, the further you get from the center, the faster things are going on a merry-go-round. And in that case, if you imagine stars fixed to the merry-go-round and you go a distance r from the center, this is what the rotation curve would look like. At the center, things aren't moving quickly at all. They're just kind of spinning and turning in place. But the further you go from the center, the faster and faster things are moving. Okay, this would be an increasing rotation curve for a merry-go-round. Another possibility is kind of the opposite. It's something we've studied before from Kepler's laws and Newton's laws, and that is what are the speeds of the planets as you move away from the sun. And you can draw a rotation curve for those, and it looks like this. Mercury is moving the fastest, and then they go slower and slower and slower the further away you get from the sun. I'm not going to rederive this, just as a reminder, this is some of the ways of figuring this out, that at the end of the day, this is because all the gravity in our solar system is all at the sun. As you go further and further from the sun, the gravity just keeps getting decreasing. Okay, there's no more mass in the solar system that adds more gravity as you move further out. So things just move more and more slowly as they get further from the sun. Okay, so this is another type of rotation curve you might expect. This type of rotation curve applies anytime all the mass is you're orbiting something where all the mass is. Okay, all the mass is here, so no more gravity, no more mass that adds gravity is being added as you move further and further away. Now, the real life situation looks like this. Here's a top-down view of a, say, spiral galaxy. And most of the stars are closer to the center, and as you go outward, there's fewer and fewer stars. And at a certain point, where this dotted line is, you don't see any more matter, right? You don't see much more stars. But you can still measure how fast things are going by looking at gas that's out here. And in this case, all the mass is contained inside this dotted line. And there you expect the rotation curve to look like we talked about here, like planets. You expect the rotation curve to start dropping off. Whereas inside that dotted line, things are different. As you move outward from the center, there's more and more mass, more and more sources of gravity. And so there's a region where there's like a uniform density where it causes, as you move outward, there's a huge amount of mass being added. And there, the rotation curve looks like the merry-go-round. The speeds are expected to increase. Then there's a region where the density is decreasing because you're getting towards the edge of the galaxy, and the rotation curve flattens out, and then it drops. So what you expect to see is as you look at stars in a spiral galaxy, you expect them to start going faster and faster as you move out from the center, then kind of level off, and then start to fall and drop. That's what you expect. Now, how do you measure this? You use the Doppler effect. This is how you measure the velocity of stars in a spiral galaxy. You can't see them moving because they're so big. They're moving very fast, but it looks still, right? Because it's so huge, even though they're moving very fast. It takes millions of years for them to actually orbit. But we use the Doppler effect. We see one side of the galaxy is moving towards us, so it's blue shifted. The other side of the galaxy is moving away from us, so it's red shifted. And the amount of blue or red shifted tells how fast it's moving towards or away from us. So we see something like this, right? We're looking at some spiral galaxy. The regions that are moving away from us are red shifted. The light is a little bit redder from the stars. The side that's moving towards us is the light is a little bit blue shifted. And how red or blue shifted tells us exactly how fast the stars are moving as we look at stars further and further from the center of the galaxy. And then that way we can draw rotation curves. And this is an astronomer named Vera Rubin, made a very significant discovery in the 1970s looking at a number of galaxies, including the Andromeda galaxy, using this Doppler shift technique. And she found that the orbital velocities remain the same with increasing distance. They didn't decrease like you expect. So what she saw is that this required a huge invisible source of matter extending far beyond the visible part of the galaxy. Far beyond the visible part of the galaxy. There seemed to be most of the mass, say, in the Andromeda galaxy, is past where it looks like the galaxy even is. Okay, we call this a halo. It's like a spherical halo extending far beyond the visible part of the galaxy. By the way, here is the rotation curve for Andromeda. You see the speeds increase like you expect, and as you look far, far away past all the visible number of stars and matter, you can look at hydrogen gas that's way out here. There's just a little bit of it, but you can see that it's moving way too fast. You expect the light, the curve to be dropping off like this, but instead we see that there must be some invisible matter way out here, indicating that about 5 times the mass of the galaxy is invisible. So this is kind of the picture of what we think the mass distribution in a galaxy looks. So here's, like, for example, the Milky Way galaxy, right? I've drawn this cartoon before. We're looking at the side view. Here's the disk. Here's the central bulge. There's some kind of randomly moving globular clusters. But like way further out, like 10 times further out, you can imagine this giant spherical halo containing most of the mass in the galaxy. Okay? We call that the dark matter halo. One thing to understand, right, is how do you determine rotation curves of spiral galaxies far beyond where there's starlight? You look at hydrogen, right? So, because there's always a little bit of hydrogen gas extending beyond where the stars are. And you look at the hydrogen gas, and it has an emission spectrum, right? Remember, emission spectra, they have these specific spectral lines, and you can watch whether they're Doppler shifted blue or red to determine how fast that gas is moving as it orbits the galaxy. Now, here's now spiral galaxies, their rotation curves are generally flat out to really large distances. suppose that spiral galaxies did not contain dark matter. Then what would you expect? Well, you'd expect that once you got past the kind of visible part of the galaxy, you'd expect the velocities of the stars to fall like this. You expect the orbital speeds to drop. And that's what you'd expect to see. But instead, we see that they're flat, indicating that there's a large amount of dark matter in most galaxies. Okay, here's a poll question for you. Now, remember, I just talked about the distribution of dark matter in a spiral galaxy, what it looks like. So here I just want you to remember, what did we talk about when we talked about the distribution of dark matter? What roughly does it look like?
Said a halo. Which one of the halo? Which halo is it? 10 times the halo is it?
All right, I'll give you 5 more seconds. All right. Most people got this right. Right? It's approximately spherical, and it extends far beyond the middle parts of the galaxy.
10 times.
10 times, but very far, much further than the visible part of the galaxy. Okay?
10 times.
For dark matter halo. Now, how do you? So here's a spiral galaxy up in the corner, but right, a lot of galaxies are elliptical, right? And what does that mean? It means that all the mass in the galaxy isn't all in this thin disk spiraling. It's just kind of a big fuzzball of stars moving in random directions. What about those galaxies? Can we determine how much dark matter is in those? Well, yes. What we do is we look at the spectral lines again, but instead of looking at as we move out from the center and see that some stars or gas are moving faster and faster and faster and drawing a rotation curve, instead we just look at all the stars all together. It's a big fuzzball. The stars are some are moving faster, some are moving slower. And if you have a larger distribution of speeds because some of them are going really fast, then you expect those spectral lines to be blurred out more. So when you look at an elliptical galaxy, you look at just, say, the hydrogen spectral line, it's blurred out. It's going to be washed out, blurred out more for a galaxy with more mass because it'll be able to contain stars that are moving fast. And in this way, we can do the same thing. We get the same information as for a spiral galaxy. And what we see is the same thing. We see that elliptical galaxies also mostly are made of dark matter. They're about, on average, 5 to 10 times more invisible matter than is visible. Now, in addition to galaxies, both spiral and elliptical, we see the same thing in clusters of galaxies, because clusters of galaxies, remember we talked about groups of galaxies and clusters and superclusters. So if we look at galaxies that are in clusters, they're orbiting each other. Okay? They're bound gravitationally to each other, and you can measure how fast they're moving. And basically, if the galaxies are moving too quickly, it tells you that there must be a source of gravity that you can't see. The same thing is true of gas. If you look at the gas in the cluster, you look at the temperature of the gas should be expanding outward because it's too hot. But instead, it's gravitationally contained by what turns out to be, when we do the math, 10, sometimes 40, up to 40 times the mass of what we can see in the galaxy. Finally, we see the same thing through gravitational lensing. Now, I'm about to talk about how we do gravitational lensing, because it's a totally different method of determining the mass inside galaxies. Here's one example of a galaxy cluster, and I'm going to talk about gravitational lensing in a second, but also this allows us to demonstrate all three of these techniques. So if you look at this, this is one of the closest large clusters to us. Has about 1,000 galaxies, about 100 million parsecs from Earth. And in visible light, this is what the cluster looks like. And if you measure the speeds of all these galaxies, they're moving too quickly, given the visible number of galaxies there that could add to the mass to hold them together. They're just moving too quickly. They should be flying apart. Similarly, if you take an image with X-rays, you see that there's hot gas in this cluster. It's the same area, but you see hot gas that's colored purple from X-rays. That gas should be expanding outward. It's held together by some amount of mass that's about 10 times what's visible. But similarly, we can map out through gravitational lensing where not only the amount of dark matter, but where it is. So here's a galaxy cluster where in purple, we've mapped out where most of the mass is. What we learned is that there's about 2% of the mass is in stars, about 13% of the mass is in gas, which you can see through X-rays. There's about 85% dark matter. And this is how gravitational lensing works. It really does work just like a lens, okay? But instead of the lens being made of glass, causing light to bend, it's the warped space-time, right? Einstein's relativity tells us that space-time itself gets bent by things that have mass, right? That's what gravity is. It's the bending of space-time. And when light from, say, some very distant galaxy tries to come towards us, if it has to pass through, say, a cluster of galaxies with a whole lot of mass, that light is going to get bent by that curved space-time. And therefore, this cluster of galaxies acts like a lens, literally. And you see pictures like this. So here we're seeing a galaxy lensed through a foreground cluster of galaxies. You see this kind of bluish galaxy here? The same galaxy is also here and here. It's being distorted all around by this gravitational lens. And you see other examples here. There's like distorted images of distant galaxies. And how much distortion tells us how much mass there is, how much gravity was able to distort the light. And the same thing, we learned that about 10 times the visible matter is some unseen type of matter that's adding about 10 times as much gravity. Here's a really extreme example. This is a distant galaxy that's getting, its light has bent it into like a horseshoe shape, completely distorted because of the gravity from this foreground galaxy. Here's another example from the Hubble Space Telescope. Again, you see all these distorted, kind of thin. It's almost exactly like you set a galaxy through a lens, right? Here, 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 here. And again, how much distortion you see tells you how much gravity there is, and therefore how much unseen matter. Here's another extreme case. This is a single galaxy being imaged 4 times. It's called the Einstein cross because it kind of produces like a cross shape. But basically, there's a foreground galaxy, and there's a single galaxy behind it, but the light from that galaxy is getting distorted upward, downward, to the right, to the left. So we see 4 copies. Again, just like you had a weird shaped lens in front of that background galaxy, we call it poison. We even have cases where not only can we measure how much and where the dark matter is, but we can actually see it separating from the visible matter. So this is called the bullet cluster because you have 2 galaxy clusters that have passed through each other. And in pink is the gas that's heated up as these galaxy clusters pass through each other. It forms kind of a shock wave, as though a bullet passed through. It was kind of that shock wave you see. And that's because that gas, that visible matter, it slows down as it hits other gas. And that's what you see in pink. But through gravitational lensing, we can measure the actual majority of mass that's mostly dark matter, and that's shown in purple. And what we see is that stuff goes faster. It moves out ahead of the slowed down pink stuff because it doesn't interact. It's invisible matter. It just keeps going like a ghost. But the pink stuff, the visible matter, gets slowed down as it runs into itself. So it's a very beautiful demonstration of the existence of dark matter. Now, one thing to emphasize is just that, hey, astronomers consider all the mundane options, right? Is it dust and gas? Well, turns out no, we can actually see dust and gas. You can see dust here very clearly in our own Milky Way. Very easy to see dust. And I'll also remind you in a second, but it's very easy to see gas because it emits light, even if it's not visible light. You can see it in other wavelengths. You can use gravitational lensing to look for like little planets, failed stars, right? Like white dwarfs, asteroids, all that sort of thing. You can use microlensing, gravitational lensing to look for little flickering. I'll give examples of that. And then in fact, cosmic microwave background totally rules out anything other than some new type of matter completely. So one thing, gas. I've shown this picture before. This is of our own Milky Way, looking at it through different wavelengths of light: radio waves, microwaves, infrared, visible, ultraviolet, X-rays. We can see everything. We can see all the gas, all the dust in the Milky Way. So it's definitely not, even though gas, like in this room, looks invisible to us, we can see it in other wavelengths of light. So it's definitely not gas, regular gas. We can use gravitational lensing to look for twinkling of stars, right? So if we think that maybe dark matter is like rogue planets, like Jupiter's or something, well, we look at the stars and we wait for one of those planets to pass in front of the stars and it twinkles. So here's just an example. Here's some star, kind of twinkles, and we measure the amount of that sort of stuff. It's called microlensing. So this tells us that actually, no, dark matter can't be this stuff. There's not nearly enough of it. Big Bang nucleosynthesis. We talk about how much, that we can predict how much hydrogen, how much helium, lithium is produced during the Big Bang. And in fact, that turns out to be very sensitive to the amount of dark matter. And when we look at how much hydrogen, helium, and lithium there is, it's consistent. So this is vertical gray line here. It tells us that there's about 4 or 5%.
Not yet. I'm in class. Go away.
Regular matter. The rest is dark matter. And then finally, the most precise and totally independent estimate of this is through the cosmic microwave background. Here's data looking across the whole sky from the light from the Big Bang. And it's in the microwave part of the spectrum. And when you look at it, you see these little density fluctuations showing in red and blue where there's places where there's not much dark matter, that's red, and where there are places where there was dark matter in the early universe that could pull matter in to lead to increased density. You have more dark matter that it has gravity. You can pull matter in and form galaxies. And in fact, when you look at the fluctuations of density as a function of scale, in other words, 1 degree scale, 2 degrees, and then going to smaller and smaller angles in the sky, you get this pattern of temperatures as a function of scale that matches theory exactly. So in blue and green is the theory, and in red is the actual data. And it's remarkable how good this fit is. And basically what you see are these little bumps corresponding to the fact that early in the universe, there's a competition between regular and ordinary matter. The regular matter, when it heats up, it wants to push out. But the dark matter only pulls in. And so you had these oscillations in the early universe where the regular matter was getting hot, pushing back out, dark matter was pulling in. And that leads to these second and third bumps telling us, based on how high they are, how much dark matter there is in the early universe. This tells us very, very precisely exactly how much dark matter there is. It can't be any regular matter. It can't be gas, dust, regular matter of any form. tells us that 85% of the mass of the matter in the universe is some new type of invisible particle. So when we talk about what dark matter is, one of our first ideas is that it's the interstellar medium. It's gas and dust. Another one of our first ideas is that it's our cute name for it is MACHO, massive compact halo object. Just means Jupiters or asteroids or dark stars, okay, black holes. But we've ruled that out. Okay? I really want to emphasize that. We've ruled that out. Another possibility is that it's neutrinos. I told you we've already discovered dark matter. Well, it turns out that neutrinos have too little mass. We've now measured that they're very, very light. They just don't have anywhere near enough mass to make up for dark matter. Not neutrino. That leaves basically a massive version of a neutrino, a new particle that we haven't discovered yet. It's basically a massive version of a neutrino. We call it a WIMP. Okay? Physicists have kind of a sense of humor. This is their, it stands for weakly interacting. So that's like a neutrino, but massive particle. Weakly interacting massive particle stands for WIMP. And that's the type of particle that we think exists that accounts for dark matter. And these WIMPs, these dark matter particles, would be produced during the Big Bang along with all the rest of the other matter. And when we do our Big Bang theory simulations, it works out. It predicts about the right amount of dark matter if we put these into our simulation. Okay, and they produce the density in the early universe that allows galaxies to form. Okay, otherwise galaxies wouldn't have had enough time to form because they wouldn't have been pulled in by gravity from all of that dark matter. Okay, so which of the following best sums up our current scientific understanding about the nature of dark matter? It probably consists, we're not 100% sure. In science, we're always, we're never usually saying things that are 100% sure. To the best of our current knowledge, we think it's some kind of weakly interacting, meaning ghostly, neutrino-like type of particle that we haven't yet discovered. That's what we think it probably is. Are there any questions so far? No. All right. So how would you search for these weakly interacting massive particles? How would you try to find them? Well, there's three main ways. One way is at a particle accelerator by producing them. We could try to produce them in the lab using E equals mc squared. Now, we do this all the time at particle accelerators. We smash particles together at very high energy. We use E equals mc squared basically to create new particles, and we hope that we create dark matter. In this case, well, I'll talk about this more in a second. Another method is indirect detection. That's trying to detect a neutrino coming from places where we think there might be a lot of dark matter that interacts and leaves a signal, like at the center of the Earth or the center of the Sun or the center of the galaxy. So you look in the direction of the center of the galaxy and look for a lot of neutrinos. That's another method. But the most direct way, this is what I work on, searches for these new particles scattering off our own detectors in the lab, the same way we would detect any particle normally. I'm going to go over these. So for an accelerator, we would look to like the biggest accelerator on Earth, say the Large Hadron Collider. This is where I actually got my PhD working in Europe. So this is what's shown as the underground circle that's on the French-Swiss border. And in one of the experiments, say the Atlas experiment, you would have particles colliding down this beam line, and then a detector that's shown in purple, where all the new particles kind of explode outward in all directions. You try to measure them all. And in the case of dark matter, if you produced a dark matter particle, well, it would just escape. That's the problem with these type of searches, is that a dark matter particle would just leave, so you wouldn't see it. But what you would see is an imbalance of energy, because momentum and energy are conserved. In this case, if a dark matter particle zooms off this way, we'll only see particles moving the other way. So that's an example shown here. We see a bunch of particles shown moving in one direction. Where these cones are, But this would imply a dark matter particle going in the opposite direction, shown in red. That's the sort of thing you'd expect to see if he's found dark matter in an accelerator search. They have not found dark matter. Another method is by detecting neutrinos. Now, neutrinos are a type of dark matter. They're just very, very, very ghostly. But our sun produces trillions of them per second, and so we can detect a few. We have these enormous detectors, like shown here. There's an example. This is in Japan. They have these enormous underground detectors. They fill with water. Here they haven't filled it all the way up with water. They're basically screwing in a new light bulb. These aren't actually light bulbs. These are all very sensitive detectors of light. And so they're on a raft servicing them, but they're going to fill that all with water. And it's a dark underground cave where they search for neutrinos. And they can contain a signal. If a bunch of them come from our sun, say, that would tell us that there's dark matter hiding in the center of our sun because it gravitationally attracted them there. But how do you detect one of these dark matter particles in the lab? Okay. Well, we exploit the fact that dark matter should be all around us, just like neutrinos are flowing through trillions of neutrinos are flowing through our bodies right now. The same thing we think is true of dark matter. Well, why is dark matter all flowing through us? Well, because the galaxy is filled with dark matter, and our solar system is moving through galaxies at 200 kilometers per second.
Get out of my class! Get out!
The dark matter is flowing through us all the time.
Get out!
What that means is that if we get really lucky and a dark matter particle bumps up against an atom, it should impart a little energy to the atom, and the atom will bounce in the opposite direction. And so we say we look for a nuclear recoil. We look for the recoil of a nucleus with a tiny bit of energy. We call it about a keV of energy. That's roughly the amount of energy as 1 billion times less than if a fruit fly landed on our detector. So we have to have incredibly sensitive detectors to try to detect dark matter. The way my experiment does it, now there's lots of different experiments. I'll tell you a little bit about my experiment called the PICO collaboration. We use bubble chambers. This is a common type of physics detector where you keep a liquid above its boiling point. So the tiniest little deposit of energy causes the fluid to suddenly boil and produces a bubble like shown here. So essentially, if a dark matter particle hits our detector, we see a bubble. So our detector, this is the same, very similar to all dark matter detectors, they're deep underground. Why? Because you want to avoid sources of contamination like cosmic rays that are kind of always flowing through our bodies at the surface of the Earth. So we go deep underground, go down this elevator, we trudge through this dark mine drift, and we eventually get to a clean room that looks like this, deep underground. Here's some students. So I have students that go with me to this lab called Snow Lab. It's in Canada. There they are. Here's one of our detectors. So this very smooth glass jar that contains a fluid that we keep above its boiling point. But you can do that actually. You can keep a fluid above its boiling point if you have a smooth enough jar. And then you wait for a tiny imperfection like dark matter to create a bubble. So here's an example of a bubble in one of our recent detectors. But we haven't discovered dark matter. No one's discovered dark matter yet. Here's one of our plots that we publish. I don't expect you to really understand it. I just want you to understand that we haven't discovered dark matter. Instead, what all of us in this field do is we keep putting out what we call limits. So what this shows is that in this whole region above these curves, we've shown that dark matter does not exist. Dark matter does not exist with so-and-so mass and so strength of coupling to ordinary matter. Any questions about dark matter so far? So another thing that dark matter does is it allows us to predict and check how the large-scale structure of the universe evolved, right? If dark matter formed kind of the gravitational seeds early in the universe around which galaxies form, right? Remember, the only reason a galaxy forms is because of gravity. And if dark matter has most of the gravity, it's going to determine where the galaxies form. Well, we can look at the large-scale structure of the universe. Where is all the matter? Where are all the galaxies? And try to understand them. So remember the cosmological principle, which turns out to be true, which is that on large scales, not in our own solar system, not in our own galaxy, but if you look out in the largest scales of the universe, it's homogeneous and isotropic. What does that mean? Isotropic means it's the same in any direction you look. Homogeneous means if you move to the left or right by a few 100 million light years or so, it looks the same. It's the same everywhere. Matter is evenly distributed, no center or edge, no preferred direction. So you look at a Hubble image like this, yes, there's matter clustered into galaxies, and even groups of galaxies, and even clusters of galaxies. But on the largest distance scales, you see thousands and thousands of galaxies spread roughly evenly across the night sky in any direction you look. This particular direction is just a tiny sliver of the night sky in one random direction. But if you look in every direction, it always looks roughly like this, roughly the same as this. And we can see overall, when we do that, we can see there's billions and billions of galaxies in the visible universe. All right, as a reminder, right, on the smaller scales, there's groups of galaxies, we call them groups, less than 50 galaxies or so. We have a local group containing our own Milky Way, and the Andromeda Galaxy, Triangulum, 54 galaxies total, if we include all the local galaxies, including dwarf galaxies. That covers about 10 million light years. If we zoom outward further, there are clusters of galaxies, we call them, that contains up to 1,000 galaxies. And here, at this point, they're still gravitationally bound. These are up to 1,000 or so galaxies that are orbiting each other. Okay. If we keep zooming outward, eventually we get to the point where we start using words like supercluster, that is clusters of clusters. And here we're getting so large that no longer does gravity doesn't play much of a role anymore. Now we're talking about the largest distances in the universe, where you look to one side of the universe and the other side of the universe. They're not gravitationally attracted to each other anymore. They're too far apart. Our local supercluster is called Laniakea. It's about 100 million light years across. That contains our local group, our local cluster called the Virgo cluster, and over 100 other groups and clusters. Here's an example of a group, galaxies. Here's our own cluster of galaxies called the Virgo cluster. It's always hard to see because we're looking out through our own stars. So I've circled a bunch of the galaxies in this cluster. This includes us, called the Virgo cluster. But we start wanting to map all the galaxies across the entire night sky. And remember, when you look out, it looks flat, right? We look out at the night sky, it all looks flat, but we want to look in 3 dimensions, right? We want to know the distance to everything. And remember, for this, we used Hubble's law. We used the fact that how red a galaxy is, in other words, how fast it's moving away from us, tells us how far it is from us. That's Hubble's law, remember? So here, this is a picture of the entire night sky and thousands of galaxies. Each one is a little dot. And the color indicates the depth in 3 dimensions based on the redshift. So red is further away, blue is closer to us. This is what all the galaxies in the universe look like when we look out across our entire night sky. This is a 3D map, right? Remember, we use Hubble's law to create this map. Right, so how do we create a 3D map of our universe on the largest distance scales? Well, each time we see a galaxy, right, we know its position in the sky, but then to get the depth, right, we use this redshift, right? Hubble's law. It's redshift, which tells us how fast it's moving away from us, and remember, Hubble's law tells us for how fast a galaxy is moving away from us, because the universe is expanding, that allows us to figure out how far it is from us. So we create these large three-dimensional maps of the universe. And when we do, we see certain structures at the largest distance scales. We call some walls, we call some filaments, empty regions we call voids. These voids can be tens of millions of light years across, containing known galaxies. And they're bounded, so imagine kind of like a bubble. They're bounded by what we call walls, filaments, kind of creating these spider web-like structures of super clusters of galaxies. And what caused these structures? Well, it's places where gravity on largest scales early in the universe collapsed all the galaxies and stars into these regions. It was seeded by the distribution of dark matter early in the universe. Because remember, dark matter is the most important because it makes up most of the gravitating matter. And what we see is that on the largest distances, which correspond to earlier times in the universe, the matter is uniform. Okay? It's only competition between gravity and expansion of the universe that creates all of these filaments, walls, and voids. And if actually there wasn't any dark matter, we wouldn't have had enough time to form galaxies. Okay? It's dark matter that formed that gravitational well in which the visible matter could form galaxies at all by 14 billion years after the Big Bang. So here, if we kind of map out in 3 dimensions, this kind of a map showing the density of galaxies. Here's our Milky Way. There's a big coma cluster I mentioned before. I showed you pictures of the coma cluster of galaxies. There's a Perseus cluster. Over here, there's the Hercules cluster. And here's what we call the local void. It's a local place where there's like a void of galaxies. And we've done these enormous surveys where we try to map out all the galaxies in the night sky. And what we see, so here's where we are, and you can look further and further away, which is also looking backward in time, remember. So if we look at from the largest distances, so out at the edges here, the largest distances and at the earliest time, so early in the universe, everything looks really uniform. You see that? It looks totally uniform here. It's only after billions of years of gravity and so space is expanding, trying to dilute things, but gravity keeps pulling things together. They look close to us now, and after 14 billion years, we've started to form these filaments, balls, and voids. Okay? So it looks more clustery closer in time due to all these galaxies that have kind of gravitationally drawn toward each other. And all these voids have opened up as the universe expands, creating more empty space. And this matches what we see when we do simulations. So you do simulations of like the whole universe. Started out with something very uniform. It starts to form these kind of filaments, spider web-like filaments. These contain millions of galaxies, and these little voids and what we call walls. And so it matches up this theory. Everything fits together. Everything seems to hold together into a coherent picture. By the way, when we map out the locations of galaxies, let me just show you kind of zooming out from where we are in 3 dimensions. So here, first of all, when you try to do 3 dimensions, I'm going to show you a couple directions because it's kind of hard to see in 3D in one picture. So here's like the X and Y. You see your Milky Way, Andromeda, and each of these things circled are like little groups of galaxies. And I'm going to do the same picture, but kind of rotate it on its side. You're going to see in 3 dimensions. So you see, actually, this is kind of forming almost like there's a cluster in, I said, a supercluster in the XY plane, but just above us, there's what we call the local void. There'll be any galaxies here. There's one up here. It's what we call a void. If we zoom out further, this is again in the XY direction. Here's our Milky Way. Here's the region we were just showing. But if we zoomed out further, we now have these clusters. We have the Virgo cluster is kind of this whole region. And we have names for these smaller subclusters here. But the majority of the Virgo cluster is a little bit, just a little bit of ways away to the upper left from our own Milky Way. If we zoom out further, the Virgo cluster is here. This is what we call a supercluster. Here's a Virgo cluster. It's a coma cluster over here. But we begin to see these larger structures. This is called the Great Wall over here. This down here is our little local void. We see other voids. This is called the zone of avoidance, sculptor void, the southern wall, and so on. And remember, all of these kind of larger structures were formed. Imagine the universe is stretching and expanding, leaving voids. Meanwhile, you have the competition because you also have gravity pulling inward to form these clusters. So that's why you kind of form these spider webs. You have things pulling in, form these clusters, but then at the same time the universe is expanding, kind of blossoming out any regions that don't have any galaxies. They get larger. Here's just kind of a three-dimensional view of that same size, kind of zoomed out really, really far, to give you a sense of the kind of 3D density of galaxies. And then not only do we, when we do these studies of the 3D maps of the night sky, not only do we get the positions in 3 dimensions, we also can see their velocity. Now, we can't see them physically moving because of the vast distances. I mean, they're moving very quickly, but again, the distances are so large that you'd have to wait billions of years to actually see them move. But their redshift tells us where they're going. So here's our Milky Way here, and here's the Virgo cluster. But on the largest distance scales, we actually see that there is like a large region of gravity centered on the Centaurus cluster. They're called the Great Attractor because it's attracting gravitationally all the local clusters towards it. So we can actually see things are moving in various ways on the largest distance scales due to the action of gravity. Any questions about the structure of the universe at the largest scales? Okay, well, finally, I want to give you a little review of the acceleration of the universe in dark energy. We talked last time about the Hubble parameter. So here's this nice plot showing, if we look at, say, supernovae that allow us to determine how far away, even far away galaxies are, because we can see that standard candle, we call it, something that's always the same brightness going off in distant galaxies. We see that the further the galaxy is away from us is, the faster it's moving from us. It's this really nice straight line that gives us what's called Hubble's law. That is, the further away a galaxy is from us, the faster it's moving from us, the more redshifted it is. And as you just saw, this is a very, very strong law. Like, that is, there's no violation of this law. It's very, very good. So we can look at any galaxy and see how far away it is by looking at its redshift. And this is because of the expansion of the universe. It tells us that the universe is expanding. So think of a raisin cake. You put a cake in the oven, it's got these raisins, those represent galaxies. But as the cake expands in the oven, the distance between raisins starts increasing. This is the same thing as if our universe is expanding. The space itself between galaxies is expanding. Now, as a result, the further any two raisins are, or the further any two galaxies are, the faster and faster those raisins are expanding away from each other. So that's the nature of Hubble's law, telling us that the universe is expanding. Not only that, but that the universe is expanding potentially at different rates, depending on how much matter is in the universe, trying to hold the universe together. So a universe that only had matter would actually start slowing down because it wants to pull back in. But there's also energy potentially in the fabric of space itself that wants to keep space expanding even faster and faster and accelerating. And that's called dark energy. And so you can imagine universes that could be expanding, slow down, and then recollapse. You can imagine universes that expand and just kind of coast. Or you can imagine universes that expand and then start expanding faster and faster until they rip apart. And one question, and then that would be a universe with a lot of dark energy. And which one is this? Is it? Well, when we look at supernovae over vast distances, we can see, because the further away we look, we're kind of looking backward in time, we can see how fast the universe was expanding a long, long time ago. We can see how fast the universe is expanding now, and we can extrapolate. And it turns out that what we see is the universe is accelerating. It was expanding more slowly in the past. It's expanding faster now. It tells us that it's kind of following this yellow trajectory. The universe is not only expanding, but the rate of expansion is increasing. So that's one of two components for our understanding the universe on the largest scales. Is it expanding? Yes. And it's expanding faster and faster. And another is its geometry. Is the universe curved in a way that we call closed? Is it curved in a way that we call open? Or is it flat? And all of this data tells us, I'm kind of just reminding you of something we talked about in the last lecture. All the data tells us that it's flat. Okay, so here's cosmic microwave background data that we talked a whole lot about. Here's supernova data we just talked about. Here's another type of data that we haven't had time to talk about called baryonic acoustic oscillations in green. They all agree that the universe is flat. And overall, the picture of our universe on largest scales is that it's flat. As far as we know, it could be infinite. There's a limit to how far we can see, which is about 14 billion light years, because past that, anything we see, we're just seeing the light from the Big Bang. But that doesn't, the universe itself could still be, the universe itself, as far as we know, could be infinite. We don't know. And finally, it's expanding, and it's expanding faster and faster. And what that tells us is that billions and billions of years from now, the galaxies will be moving faster and faster away, to the point that people who live a few billion years from now will look out at the night sky and they won't even see galaxies. We're kind of lucky that we can even see another galaxy, because at that point they'll be speeding away from each other so fast we won't even be able to see any other galaxies. Finally, when you talk about the matter in the universe, most of the matter is a type of invisible matter that we think, in a decade from now, you'll probably see in the news that we discover, it's a new type of neutrino-like particle that we just needed a more sensitive detector to discover. We're not 100% certain. It could be that we just don't understand gravity well. It's possible. But there's something about the universe that we don't entirely understand. It seems that on the largest scales, gravity is stronger than we think. And that's likely due to just some invisible matter that we call dark. Any questions? All right, well then I will let you go. And like I said, I need to remind you on D2L, but I'm going to cancel next class due to a family health emergency. I have to go to a bunch of appointments all Wednesday. So we will have class on Monday. So we'll have one more class 1 week from today. Everyone have a good day or good week.
Thank you.
Thank you, Professor.
Yeah.